In this video, we're gonna give a quick review of how to solve equations and inequalities graphically, and then we'll give one motivation for the concept of limit. Let us start by coming back to our big picture. Remember, we said that our main objects of studies are functions. But what exactly do we want to know about them? Say you meet a very cute function at a party. What kind of questions can you ask? Well, that really depends on your vocabulary. At the high school level, you can say things about the values of the function. After this course, you'll also be able to talk about limits, derivatives, and antiderivatives, and so on. And as we mentioned in class, we want to understand these things both algebraically, in terms of formulas, and also graphically. We won't talk about derivatives until next chapter, but you have seen in the video I assigned for homework the visual manifestation of first and second derivative. Somehow, they should capture the way a graph curves. But let us forget about that and focus on the immediate future. We're gonna officially introduce limit on Friday. So today I want to show you its visual manifestation and at the same time give you one motivation for it. To do so, let us quickly review how to say things about values of a function from its graph. More specifically, given a function f, we are often interested in asking questions like when is f equal to 2 or when is f bigger than 2. Actually, there's no reason why we can only compare f with constant. We can also compare f with other functions. We can ask when is fx equal to, say, x squared, and when is fx strictly bigger than x squared. So now let us quickly review how we would answer these questions by looking at the graph of f and x squared. Consider the following love story. Let's say we can somehow quantify attraction, and we graph his level of attraction through time compared to hers. Let's denote his level of attraction by f and hers by g, both viewed as functions of time. You see, at the beginning, in month 0, boy meets girl and he likes her way more. However, after 9 months, it seems that his attraction has gone down and she is way more into him than he is into her. Now, so if I ask you to solve this equation to find all x such that fx is equal to gx, what does that mean in English? Well, observe that x here denote time, and this is asking when is his level of attraction towards her exactly equal to her level of attraction toward him. If you look at the graph, you see that happens during the first month, 4th month, and 8th month. So you'll say the solution to this is x equal to 1, 4, 8. As a mantra, you could say solutions are the intersections. But you should know that phrasing is not exactly accurate. You should say that the solutions are the x-coordinates of the point of intersection. Alright, so now what if I ask you to solve this inequality? How does this translate into English? Well, this is just asking you when is his attraction toward her more than her attraction toward him? When did he like her more than she liked him? Well, let's see. Observe that here you see during the first month, he definitely likes her way more. And then he got more emotionally invested again between the 4th month and the 8th month. You see visually that corresponds to when his graph is above her graph. Now here you have to be a bit careful though, because what do you mean by between? Some of you will write the answer to this as follows. And what's wrong with this answer? Well, if you look closely, we are asking you when did he like her strictly more than she likes him. You cannot include this 1st month, 4th month, and 8th month because that's when they like each other equally. Right? We're asking for when does he have the upper hand. But during month 1, 4, and 8th, they are equally invested, so we have to exclude that. Thus your answer should be during the 1st month, but non-inclusive, right? And between the 4th and 8th month, non-inclusive. Alright, so that's a quick review of how we would solve equations and inequalities graphically. Roughly speaking, we solve equations by finding points of intersections, And we solve inequalities by checking when one curve is above or below the other one. It seems that just with values of the function, we could already say a lot. Why would we need to introduce new terminologies like limits? Well, if we want to continue with the romance analogy, we'll see that in reality, attraction does not always look like this. Or if not real life, then at least in many Korean dramas, there is often the following ridiculous situation which sends a very bad message to teenage girls. The guy started out being very cold and disinterested toward the girl, and then the girl goes and get a makeover, maybe plastic surgery or magic, and then boom, suddenly the guy is super interested. Now, what's different about the development of the level of attraction of this guy versus this guy here is that there is a sudden jump in this guy's feeling here. He just go from hate to love, from distant to infatuation, and there was nothing in between. Whereas this guy here, he goes from hot to cold, but he experienced all the degrees in between. At some point he was lukewarm, and then he went cold. Mathematically, we would say that this function here is not continuous, whereas this function here is continuous. Alright, now, colloquially, we often say his feelings jump from 0 to 100. So let us try to translate this into mathematics. Now, I didn't make the 0 here, so let's say, during the 3rd month, his feeling suddenly jumped from 2 to 100. Now, how would we express that symbolically? If we view his attraction as a function of time and denote it by fx, then what does it mean to say that right here, right at this month, his feeling jumped from 2 to 100? Well, we know that the value of f right at 3 is 100, right? His attraction right at that moment in this 3rd month is 100. And we know how to express that symbolically. As we've said, you know how to talk about values of a function at a point. But then, how do we talk about this number 2 here? Because that's not the value of this function. This is not f of 3, right? It's not how he feels toward her at this moment in time, right? At this moment, he feels really strong attraction. So here's the way you want to think about this too. You should think of it as how much he would have been attracted to her had she not had the makeover. Had she not had the makeover that day, then right at this moment, his attraction toward her would be exactly 2. So we want a way to express this symbolically and mathematically. And we can't use the value of the function. Because again, this number 2 here is not how he actually felt at that moment. It's kind of a counterfactual. It's not exactly what he felt at that moment, but what his feeling was approaching at that moment. So we call this the left limit of f at 3. The limit of f as x approaches 3 from the left. Right, so we write limit of f as x approaches 3 from the left. That's denoted by this minus sign. Now, of course, as you expect, there is also limit of f as x approaches 3 from the right. And can you guess what it means? Well, imagine that right at this moment when he saw her makeover, he felt extremely passionate. The attraction score rise to 120. But just right at that moment, and then right after that he calmed down, he immediately calmed down, and his attraction went down a bit. Then you would say that f of 3 is equal to 120. And here, based on this picture, you would say that the right limit of f at 3 is equal to 100, i.e. the limit of f as x approaches 3 from the right is equal to 100. And you can think of it, roughly speaking, as his level of attraction toward her right after this moment at 3. Now, if the left limit and the right limit at 3 are equal, then f is said to have a two-sided limit at 3, and we usually just say f has a limit at 3. In our picture here, the limit of f at 3 is equal to 100. What happened here is he had a crush only in one single moment, one single instant, right? And the rest he's pretty consistent. Now, if additionally this f of 3 is equal to the two-sided limit at 3, then we say that the function f is continuous at 3. That is, right at this moment, during this third month, there was no abrupt change in his feelings. They were just going with their natural course. Alright, so that's some graphical intuition for the values of the function and limits of a function. On Friday, we're gonna formalize the notion of limit, and I'll give you a different analogy for you to understand the delta epsilon definition.